Hello everyone, welcome to this new tutorial about grid connected PV system, where in this tutorial I will explain how to build the PV system in PSCAD from scratch, from PV module then up to PV system, how this system is connected to the grid, and also how the maximum power point tracking is applied in PSCAD. So let's start. First, I will use a PV module which is from Kyocera KC200JT. This module that I'm going to use, which is each module produce 200 watt. So this module will be modeled in PSCAD using single diode model. This is the single diode model. So I need to identify the resistance, series resistance, parallel resistance, the diode parameters, and what is the photovoltaic current. Let's start. So this is the specification of this module. We can see how much the maximum power and the maximum power voltage, current, maximum current, and the open circuit voltage, short circuit current, and what is the maximum system voltage, which is important. So we cannot design PV string higher than 600 volt because the installation will not handle more than this voltage. We can see also this company provided the normal operating condition, this one, which is important for if you want to design the photovoltaic model based on the data sheet that the same that I did. You can see the number of cells in the module is 54, and all these cells are connected in series. This is, we will see how it will how we will use it. So this is my paper that published in Transaction Energy Conversion, how to model this PV module, and these are the optimal parameters of the photovoltaic current and the saturation current, ideal factor of this diode, series resistance, parallel resistance. This is for module, but in PSCAD they require for the cell. So I will explain now how to do it. So now we can see that for the how to design, for example, 100 kilowatt peak system using this PV module, we know that number of modules that required, because we have 200 watt and we have 100,000 watt for the system. So how many, or the total number of the modules that required? Almost 500. So some of these modules will be connected in series, some will be connected in parallel. So we will make n equal n series times in parallel. In series will be restricted by the maximum volt, as we explained. So 600 divided by the open circuit, because for sure we care about open circuit voltage. So we have 18 cells will be connected in series. Then the number of parallel will be 500 over 18, almost it will be 28. So the operating voltage now, because for the series the voltage will increase, but for the parallel the current will increase. So for the series we will multiply the maximum voltage here in this for module. So all these will be times 18, then it will be 473. Same for maximum current, and same for the open circuit voltage and short circuit current. This is the total V open circuit and the total of the short circuit current. This is why I am explaining, because these are required in PSCAD, so this is why I explained here. So for series and parallel resistance, we know that RS total is equal number of series over number of parallel times RS, and for RP total approximately it is RP over NP. So for the module, if we want to look to the cells, as we explained that the number of cells is 54, but all are connected in series, these cells, so number of parallel equal 1. The PSCAD requires RS for cell, not for module. So for cell, we will multiply by NB by NS. This we will make we will multiply NB by RS total, then divided by NS. So now we have RS for module, as we discussed previously, that I designed RS for module 0.4, but for the cell it will be divided by 54, so it will be 0.07. And for R parallel cell, as we know that NB equal 1, so times 1, it will be for the same value we will use. And for the saturation current and the short circuit current, because all are connected as we explained in series, so the current will not change. So for I cell, it will be the same of I0 module that I designed previously in here in this paper. So now if we want to go to the PSCAD, here we will make, for example, new project. I will call it, for example, BV system, like this, for example. And now I want to use the BV cell. We will find BV cell here in this module, which is the main sources. And we can see here that we have this BV cell. So I'll copy this one, copy and go to the BV system. Okay. Now, this is BV array. We can see number of modules connected in series, number of modules, string in parallel, then number of cells connected in series per module. This is the point, that and number of cell strings in parallel per module, reference irradiation and reference cell temperature. These are, and here we can see the BV cell temperature, equivalent area per cell, series resistance per cell, and those things as I explained previously. For example, if I want to design the 100 kilowatt system, I will use, for example, as explained, 18 in series, and those strings will be 28 in parallel. For the cells per module, we know that connected in series, so it will be 54, and here it will be 1, so I will not change this one. Then we will go here, the effective area. We will divide the whole effective area by 54. So this will be, for example, if we go to the specification and we will see, for example, here, this is the specification. We can see the area here, the area where we have the length and width, 140, this one 140 meter 9. So we will divide by 54 and we will know how much the cell area. Series resistance per cell, as I explained previously, it will be 0.002. Shunt resistance is the same. So here I will show you now the system that I already modeled. This is BV system, BV1. So you can see now this is the PV array. This is it will be 18, 28, 54 for this is per module, and here we can see the area that I calculated per cell, and this is series resistance as explained 0.07, same shunt resistance 490. This is the diode idling factor that I calculated 0.95. This is the band gap energy, which is for the silicon, and here saturation current, which is in kiloamps, so I make it minus 13. Here also in kiloamps the short circuit current, so you should be careful about this. And the temperature coefficient of photocurrent, we know that this is the same temperature coefficient for this one, for I short circuit current, this one 30.18 ampere over degree Celsius, but here you can see that this is not ampere over degree, it is ampere over Kelvin, so it is the same. You can consider it or you can convert it. Now after that, first of all, I will examine the PV array that it will produce for at radiation 1000 and temperature 25. It should produce 100 kilowatt. So the measurement is in mega volt ampere, so it will be 0.1 maximum. So for this, let's start to run this one. Here I tried to change the voltage from, you can see this is open circuit voltage over 2. So here I tried to generate a signal changing from 0 to the total open circuit voltage here, which we explained previously. It is point, here you can see it is 592, but here in kilovolts, so it will be 0.5. So see, we have this one is 0.5, almost 0.59 kilovolt. So I tried to make a step change from 1000 to 500. So you can see now, once it converted from 1000 radiation to 500 radiation, we can see how much the output is almost 0.05, higher than 0.05. It is 0.054. That means this is 5, which is almost 54,000, because the total is here is 100,000 watt or 100 kilowatt. This is now, it will be 50 kilowatt or 54 kilowatt. So now this is the PV characteristics. You can see how to create this PV characteristic. I think you know about it, but I will explain. You will make this XY plot here. This is the XY plot. Then sorry, I will erase that one. So this is the XY plot, and then you can add, for example, in X coordinate it is voltage. So this one, you will make this one, add as a curve, then go here and paste curve. Why I started by voltage? Because if I started by power, it will be, the power will be in x-axis, but I want in x-axis the voltage. Then here, this is the power, so I add this as a curve. Now paste, see, now the power, it will be in the y-axis, and this is how I draw or plotted this this curve. Now after that, we created the PV array. This is the PV array system. Now I will go to the how to make the MPPT. That means we need DC to DC converter. So this is the, now this is the how to make the DC to DC converter. I used BOS converter. Why? We used BOS converter because we need higher voltage in the DC input of the inverter for stability. So for example, I want the AC voltage is, I want 400 volt. This is line to line. Okay, so if I want 400, how to design the DC voltage? You can see here the DC voltage should be higher than this line to line times root square of 2, so it will equal 566 volt. So I can assume that my DC voltage is, for example, this is the famous one, which is 700 volt. So how much the duty factor? This is duty factor. How much the duty factor? It will be calculated that V out equal V input 1 minus D, then it will be calculated, it is 0.32. So now I know the duty factor. Then how I will design this L and how I will design this C. The L is responsible for smoothing the current. So if I want the current 10% of the I base, so how I will calculate I base in this side, I should use the voltage, the maximum voltage of the PV array. So it will be 100,000 over 470 volt. So this is the ripple that I will design L for it, for example. So the L of the Boost converter, this is the famous function. It is V input times D switching frequency, and based on your frequency you can change the value of the L Boost. If you want higher frequency, lower frequency, you should be careful. And for the C, the capacitor, it is responsible for smoothing the DC voltage. So the capacitor is I out, which I out here is different, which is 143, because it is different from the IN. This is the IN. So I out, you should be careful that I out is P out over V out. So V out here is 700, so it will be 100 kilowatt, for example, over V out, which is 700, not 400. So you will find that it is equal to this value, which is 143. So we designed, this is the CDC. Now I will go to PSCAD and I will show you this DC to DC converter here. Now I don't need this one because I already have. I will delete it. So I forget usually to erase these calculations. So now the same PV array, I designed this. You can see here this one. This is the DC to DC converter. I tried to make it higher here, 3.5 milliampere for more smoothing. And this is 1000 microfarad. This is the capacitor. And this is the array. You can see this is the array. Okay. So now how to drive this this switch? We have this IGBT. Now I should drive it to achieve maximum power point tracking. So now I design. There is two steps. We have MPPT, which is already built in the BV in the PSCAD. This MPPT is using either incremental conductance or perturb and observe algorithm. So we have two algorithms. You should be careful here, as we discussed previously, that we need the PV array short circuit. This is the PV array, which you should multiply point. I will come back here and you can see This is the I short circuit. Here you can see this one. So this one is I short circuit that I should put it in the PSCAD. And also the PV array open circuit voltage, which is 0.5, because this is in kilovolt, not in volt, but in volt it is 500. So you can see now this is 592 volt or 0.59 kilovolt. So these are important to put them in the MPPT. And the initial value of VMPP, which we calculated, is 470. So it is here in kilovolt. You can see this is kilovolt. You should be careful here. This is kilovolt. So this also the sampling interval, because if you want the MPPT faster or slower as you want. Here, for example, I make it 0.01. You can make it less or more as you want. This is for actually stability. And we know the PV or the solar radiation is not fast. It is slow, so you can use slower. For example, you can make it 0.001. You can make it 0.1 as you want. And here to measure the MPPT voltage, this is the output, and here also how to calculate the PV power by multiplying PV times IPV. So now I will go from this MPPT voltage. It will be the reference value for this controller to control the VPV output of PV system, and this is the due-to ratio D1, and this due-to ratio is go through the pulse width modulation here to generate the drive signal of this IGBT. And if I want to make that this is MPPT, the output of this MPPT, which is built-in MPPT, this one is built-in. Okay, so I will run now this here, for example, the system, and you can see I don't care about that one. I care now about this one. You can see now it started from 1. This is the output power. It started from 1000. You can see it is now tracked by the MPPT that is built in PSCAD, and I'm using incremental conductance algorithm. So you can see now, for example, it is now this is the output, and you can see how the step change. It is not realistic in sometimes, unless there is fog or there is shading. So you can see now, as I explained previously, that the maximum should be more than 0.05, which is 50 kilowatt. You can see now this is the tracking. And you can use also you can change from incremental conductance to the perturb and observe, and you can see the output. And for the engineers, I recommend only to use, for example, these, because they are sufficient. This is sufficient for your projects. But as a researcher, sometimes you are looking for better performance, so you can use any algorithm. Here I designed this gray wolf, the same gray wolf algorithm, but I make it for this project. So I added this delay samples, because you can see here in the MPPT they are using a sampling interval. This is to make or to allow the system to have enough time to track them in MPPT. So here I added this delay samples. It is 100, or you can say this is 0.01, for example. as in MPPT, and this is the total number of runs. So I added also in this, I make this dimensions is 2 because if you want the system to work, you need to make more than 1. So I need only 1 dimension. This one is controlling the VM, which is MPPT. Same, or you can use directly the D2 ratio. So you can make this D2 ratio, and you will change here in the lower and upper limits. Here, the lower and upper limits that I am using here, they are for V open circuit. This is the maximum, and the minimum, instead of 0, I make it, for example, 0.1. You can make it 0, but it will not reach this value. But the most important is V open circuit. But if you want it in D2 ratio, you can change this one from, for example, 0.1 up to 0.9, for example. So this is the point here. I make it VMPP as a reference, as output from gray wolf. This is the BV. Also inside the gray wolf, instead of minimization, I change it to maximization by changing some parameters. You can, I will share with you this model, and you can see how it is different from the previous one. And now, instead of VMPPT of the built-in in PSCAD, I will use the gray wolf output, and let's see the output P array using this one. You can see now how this changing. You can see now this changing, and then it harvested the maximum power, and you will see that there is some variations. This is because randomness. So if you want to improve this one, you can do it by, as a researcher by yourself. And you can see now, once it changed to the 500 watt instead, 500 the radiation, instead of 1000 watt per meter square, it will be now 500 watt per meter square. Here I use this step. You can see it changing from 1000 to 500. So you can see now how the MPPT is working. Okay, now after that, after designing this system, I'm going to apply this one to the MPPT that is connected to the grid. You can see here, this is the BV array that is connected through DC to DC converter, then to across inverter and LCL to the grid. Now, the same that I did in wind turbine, I'm going to design this controller by using optimization, and design also the same LCL filter and the shift angle of the PLL for best operation. But now it is connected to BV array, not the wind turbine. And this is the DC to DC converter. And also same, I am using also braking resistor to protect the system from the over voltage. And you can see this the same, that you can use either MPPT of the built-in, or you can use the MPPT of the gray wolf as you want. You can see also I am using 5000 Hertz as switching frequency for the BOST DC to DC converter. These are the value of that are already I did optimization, and I will show you now how to do it. Now here you can see this is the same as I did in the wind turbine. This is the gray wolf for BV system. You can see that I'm using 13 and I'm using 500, and this project is master and the other one is slave. You can see here I'm sending the optimization variables to the project, and I am receiving the objective function. Here you can see this is the objective function that I'm sending to the gray wolf algorithm here, and these are for storage that I'm using. This is for storage, and you can see that I'm extracting the best here to monitor the best. And here you can see now for the optimal optimal I'm using now X best here. How it is better that I'm using X best? Why? Because this will store all values through all runs. So you can just add by this add overlay graph with signal here. It will be X best, and it will store all values. You should be careful that all values are recorded. And now I will make this simulation, and this is the MPPT that here I am only using the built-in, this one, which is the built-in. You can use perturb and observe, or you can use incremental conductance, any values. And after that, you are designing, either you can use the same that we designed previously here, which is 1.4, or you can use higher value. So let's just use this 1.4. And if you want to run this one gray wolf and this one only, if you want to run only this one and this one, you need to go here to the simulations, and for this one optimal BV, you are going to make a run set. You can see here run set, and your system will start doing optimization here between gray wolf BV. You can see that now I am monitoring the X best. You can see here I have almost 13. So be careful that all these values are ticked by this true. If you didn't tick this one, it will not appear here. And once you can see now the system is now changing, trying to find the optimization value. So once you get the best value, you can copy all these, copy all here, and you can use Excel sheet and paste them there. Once you copy all, for example, now I will copy all, and once I go to the Excel sheet, be careful to use this paste special. So paste special, use CSV, and here this is just for 2 iterations. If it is 500, you will paste all 500. You can see, and how many they are, 13. Can see here 13, 13. The count is 13, as it is clear here. Okay, now after finishing your design and getting the best values, I'll stop this one now. You will save this one, your project, and save it in another project. I use this one as MPPT BV optimal, and then these X value that are coming from the gray wolf, you can see here, these are coming from gray wolf here. Now I will create, instead of it, here I'll create a module. See, this module include, if I make edit definition, it is including this are the optimal values that I achieved previously. How you will do it, just create this module, then go to your Excel sheet and just copy, for example, this one and paste them. For example, I will show you now. Here, for example, I will make enter. Okay, for example, I make, because this is the output xv, so it will equal, and now I will paste this one simply. See, now I will, it will not work like this. You should make it like comma, then there is no space, then also here comma, then no space, same comma, no space, and do it for all. So it is simply. Now I will go back. I will try to make sure that this is not changed by making build. So any change, as I told you, any change in these modules, you should build first before you go to run. Now I will make sure that now the PV array that is connected to the grid is working. You can see that I am using the output optimal PV as a reference to the, instead of using here DC voltage as I used in grid connected wind turbine. Now here I am using, you can see that I am using now PV, you can see, and 0.1 is the base, which is 100 kilowatt. If you make it as a mega, it will be 0.1 megawatt. So this is the point here, and you can see this is the P optimal. This is the P optimal. Also, I should divide it by the base value, which is 0.1, and now I'm controlling the reference power, optimal power that is coming from the MPPT. So now you can see now I'm going to run this one. I'm using the MPPT, the built-in MPPT here. You can see that this is the MPPT that I'm using. This is after optimal design, and it is not the full, you need to do it again. So you need to do optimization again based on your scenarios, that if you want to make scenarios of, for example, solar radiation change. So here I am using only single value. You can see here, this is the single value of the solar radiation, which is 1000, and the temperature is 25. I didn't change here, and this is connected to the grid, and there is fault because I want to optimize the system during fault. So here I am trying to make sure that my low voltage ride through is optimized, because now I am using this fault. So once I run this system, you can see here, now I will run the system, and you can see this is the output power here. And this is the output voltage. This is the voltage. This is the power. You can see here I'm getting almost 100 kilowatt or 0.1 megawatt, you can see here. So the MPPT is working very well, and I'm waiting now till, because I make the fault at 10, but during the optimization I make it faster. You can see here this project now, you can see I am using 20 seconds, but for the optimization process in MPPT I am using only 4 seconds. This is to make the optimization faster. You can make it 5 seconds, 10 seconds, as you want. It depends on your scenarios that you are looking to optimize it. So you can see now, once this reach 10 seconds, there is a fault. It will happen, and you will see how the low voltage ride through is working in this system. And based on your different scenarios, you can change in the system. This system that actually I did the optimization only at 1000, and this is and I think it requires to do the optimization again, but at different solar radiations, especially if the solar radiation is very small, such as instead of 1000 you can use 300, and also the temperature for sure. You can see now this is the fault. This is the fault. You can see this is the low voltage right through. Here you can see, and also you can see that this is the power. It come back to the optimal value. This is all that I did in this project, and I will share this project in the, you can find it in the description. So I hope that you don't forget to subscribe in this video, in this channel, for more videos if you want, and I will try to upload videos at every weekend, but please let me know if you want me to, for example, to explain something specific in PSCAD. Thanks.